that we call the critical point, and I will say a few words about it a bit later in the talk. Actually, what really characterizes a phase transition is that a small variation of an external parameter, such as the pressure, the temperature, electrical field, magnetic field, can actually induce very strong changes on the physical properties of the material. And I actually will show you a few examples that are very well known, such as the structural phase transition. For example, the transformation from graphite to diamond. As you all know, graphite is a soft, opaque solid, and when you apply pressure and temperature, very high pressure and high temperature, you can transform it. It transforms, it undergoes a phase transition to a crystalline, transparent crystalline super hard solid, as you can see here. And this is actually related to the transformation in the atomic arrangement. So graphite, the atoms are arranged in an hexagonal lattice, while in the diamond structure, the atoms are arranged in a cube. Okay, this is one example. And also we are very familiar with the transformation that is called superconductivity. In this case, if you take a material metal, typically superconductor metal, and you actually reduce the temperature to arriving at a certain temperature that we call TC, the critical temperature, then suddenly the resistivity of the material goes down to 0, and you end up with a so-called superconductor state. In the same manner, actually, you have superfluidity in helium. In this case, you go from a liquid, a normal, so-called normal liquid, to a superfluid liquid by actually reducing the temperature to a certain temperature that we call T lambda. And in this case, you have a drop in the viscosity that goes down to 0. And there is this famous image where you could see the helium actually flowing along the edges of this vessel, for instance. Okay, this is a very classical example of phase transition. So we are all actually familiar with this with phase transition. It is very intuitive phenomenon. But at the same time, phase transition actually is also a very complex field of research. And the reason why is because it's a typical n-body problem where you have a large number of interacting particles, and basically you cannot neglect these interactions. So a very complex problem. And it concerns, as I just showed you before, a large variety of systems, type of interactions, parameters to induce such phase transition, also the thermodynamic parameters that are affected, and the orders of magnitude. And I would say that despite this diversity, this variety, it is it's remarkable that this field of research also presents great unity, the unity of concepts, and also universality of a large number of properties, such as the critical properties. Okay, and because of that, it was proposed to classify the phase transition according to the Arendt phase classification. You can have first order phase transition, second order phase transition. In this case, in the first order transition, you have the discontinuity of the first derivative of the so-called Gibbs free energy, which is a thermodynamic potential. But in other terms, it's a discontinuity in the volume, for instance, or in entropy. And for second order transition, you have the first derivative that are continuous, but you have a discontinuity of the second derivative of the Gibbs free energy. In this case, for example, the specific heat. This is actually illustrated in those two graphs here, where, for instance, you have a first order phase transition where you see that there is at a certain temperature, you increase the temperature, at a certain temperature TC, for example, you have a jump in the volume, and this is typically first order. For second order phase transition, you would not see any volume change at the transition. I will show you actually examples of such a type of phase transition. And for a second order phase transition, again, in the case of helium, when helium goes from the normal to the superfluid state, it undergoes a phase transition, of course, that is where there is no volume change, but you have a singularity in the specific heat, as you can see here. As you can see, the shape, it looks like a lambda. Actually, that's why we call this transition the lambda, the famous lambda transition. However, this kind of classification is really macroscopic, provide macroscopic description, but does not provide any microscopic insight into the origin of this type of transitions. Also, I cannot talk about phase transition without saying a word about the Lambda theory, which is probably the most common and most famous theory. It is actually a phenomenological theory, which is based on the notions of symmetry and other parameters. And it was extremely powerful and successful for explaining and predicting a variety of phase transition, including the one I just presented, the superconductivity and superfluidity. However, this kind of description requires, of course, the existence of symmetry relations between the phases that are involved in the transition and important phase transitions, such as the one that are actually very familiar, where you are very familiar with, such as the liquid gas, the glass transition, or melting, are not actually properly described by such a transition, such a theory. Sorry. Okay, so this is all I wanted to say about the general framework of phase transition. I will now move on to what I consider as potential impact of the EBS for exploring extreme states of matter. And such a topic is actually developed at several ESRF beamlines that are actually listed here to apply a large variety of techniques, such as X-ray diffraction, X-ray absorption spectroscopy, inelastic scattering, nuclear resonance scattering, and this to study the electronic, magnetic, and structural modifications that can occur under extreme pressure and temperature conditions. Okay, and if I talk about EBS, what EBS should bring as a first approximation is that it will bring a much smaller beam spot, higher beam intensity, and coherence to probe smaller and more complex sample. And in the case of high pressure experiment, very important is to have much smaller beam spot and much higher intensity. And this is actually achieved at several beamlines. that just give you two examples on ID18, where they developed the so-called nanoscope. In this instrument, they will be able actually to reduce the beam size from 10 by 10 micron to something that is close to 0.15 by 0.15. So this is actually an improvement of more than 3 orders of magnitude. So a huge improvement. The second example is that I know very well is ID27 that will actually undergo a full refurbishment in the next year, basically. And we expect for this instrument a reduction also of Morse factor 10 in both directions for the beam size, but also a flux increase of 2 orders of magnitude in monochromatic and 3 orders of magnitude in pink beam. And I will say a few words about what I mean by pink beam operation. Actually, this was, I would say, the dream performance that we defined before EBS, but now we can actually talk about the reality because a few months ago, we were able to actually collect the first preliminary result on the actual machine. And here in this image that was collected at about 30 meters from the source using the so-called U35 undulator, you can see a very nice beam profile that is about 1 millimeter in diameter. And this is to be compared with the size in the horizontal direction before EBS, which was about 26 millimeter. And as you can see, there is an important compression along the horizontal direction that is actually related to the outstanding performance of the new machine by reducing the horizontal emittance. And I would say that I would use this opportunity actually to congratulate all the people involved in the EBS projects, because this is an outstanding, really outstanding achievement. If you think that they removed the full ring and put it back in place, they put a new ring a year later, and they could actually obtain this very nice performance in a record time. And actually, in the case of ID27, I can say that the beam was injected about 300 micron away from what it was expected, meaning less than 10 microradiant, if you see at the angular deviation. So this is quite amazing performance. Not only the shape of the beam, but also the energy distribution in this beam, as you can see here from the undulator spectrum seen through a silicon 111 crystal, is also very nice and as expected. And if you zoom on one of these harmonics here, you can see it here. It's very nice harmonic that is actually highly symmetric and with a very narrow bandwidth of 0.5% at full width of maximum. And this is a very nice feature that we will fully exploit, because if you look actually at this image here, which shows a direct from ID13, it's a different ESRF beamline, which shows the reproducibility of the result actually. You can see that the first, this harmonic is actually very nice now. And if you compare it to what it was before EBS, you see that not only it was a bit, it was larger, but also it was highly dissymmetric. And actually, if you want to perform experiments such as diffraction experiment, this is extremely difficult to do it with this kind of beam energy profile, because this will be actually translated in the diffraction pattern and it will be extremely difficult to correct. Okay, so that's very good news. And also the fact that we could work directly with this beam that we call the famous pink beam, we could actually gain a large amount of flux. So this is in this mode that we could gain more than 3 orders of magnitude more flux than before, with an energy resolution that is quite good. 0.5% is 510 to the -3. So we can actually do a nice diffraction experiment in this mode. Okay, and this is on the side of the machine, but also now we have collected also some result on the experiment on the experimental side. And what you see here is a direct image of the source through KB mirrors at 33 kV. And as you can see, it is a very nice roundly shaped beam that is actually very close to the theoretical values, which is in this case 2.1 by 2.7 micron, and is only limited actually by the mirror stoppers. When we will install the new mirrors, we will get a compression of a factor 10 of these values. So that's really, really promising. So, and also I would also add that this beam is very stable and I mean, can already be used, and that's why it is optimistic to say that the user operation will resume quite well in August. Okay, with that, I will now say, okay, that of course, now we have a nice beam, so we have no excuse for not performing the best possible experiments. And I would say that one of the field that is natural for this kind of machine is for exploring extreme states of matter. And one of the standard subject that is a long-standing subject is, of course, hydrogen, that started 2 decades ago on 99, and they gave excellent results. And more recently, actually, the subject was also revitalized by what we so-called the possibility to synthesize and study metalhydrides, and I will explain you why. So if you look, actually, hydrogen is a very fundamental material that was actually explained. You could explain all the physics of the 20th century through the atom of hydrogen, because it's the first, also simplest and most common chemical element in the universe. It is, as just said before, very interesting now because the recent record superconducting temperature, TC, of about very close to room temperature, actually 250 and 265 Kelvin, was obtained in metalhydride. And this is actually due to the properties of atomic hydrogen that is enclosed in a sort of metal sublattice and actually plays as electron donors. And also, but today I will tell you a bit more about a very old story, which is so-called the Graal of high pressure physics, which is the possibility to metallize hydrogen. So I can illustrate this. If you look at the pressure temperature phase diagram of hydrogen that is here, actually hydrogen has actually a rather complex solid polymorphism in this region up to 300 GPa, but more interesting, and I think why the people are so interested in hydrogen at the moment is because there is ab initio, also ab initio simulation that predict an insulator to metal transition at about 450 GPa. And if you increase the pressure by 100 GPa more, there is a prediction for a molecular to atomic transition, also in the metal state. So, of course, this is easy to represent and it's probably easier to do with ab initio simulations, but for experiments, it still represents a huge challenge. To give you an idea, here is 350 GPa that are represented here. For the people that are not familiar with this field, is exactly the pressure that you have at the center of the Earth. So basically, the challenge that you have to perform is to produce enormous pressure. And to achieve this, you have to work with extremely small sample. And the device to do that is actually the diamond Anvil cell. And actually, here I show you a recent example of development, which is a toroidal diamond Anvil cell, because classically, the diamond Anvil cell in the standard shape, the maximum pressure that could be reached is in the order of 380, 400 GPa maximum. And this was a limit because it is below the metallization of hydrogen. But with this new device, it was actually recently developed in collaboration between ESRF and the Paris group, with Agnès Devel and Paul Loubert. They could achieve by actually a new shape that are toroidal shape, actually that can, with this shape, you can reduce the stress on the diamond and actually reach much higher pressure, such as 650 GPa. And this is actually an excellent news because it is actually located well into the stability field of metallic hydrogen. And the second advantage of this is that it enables the confinement. Confinement is a word that we should not employ, but this is hydrogen confinement is possible in this kind of device. Okay, so and this was actually achieved 2 or 3 years ago. It took some time actually to be able to solve some technical problem, load hydrogen, and actually do some quantitative measurement. And this was actually achieved by the group of Paul Loubert this year and published in Nature a few months ago. So I invite you to read this paper, very nice paper, where you have actually, you can clearly see the transition from infrared, from the collapse of the infrared intensity at about 430 GPa. So beyond the limit of the standard diamond Anvil cell, but just fully in the field of accessible by the toroidal Anvil. So, and in this case, they could actually assign this transition to an insulator, a metal transition. And this was actually evidenced by infrared spectroscopy at Soleil. And now it's more or less established that hydrogen is in its metallic phase, but there is still some open questions, such as what is the nature? Is it a molecular solid or an atomic solid, as predicted by the ab initio simulation, and what is the structure of this metallic hydrogen? So this is actually quite difficult questions to answer, and for this we will really need the very intense nano beam of EBS to perform, for example, diffraction experiment and other type of characterization experiments. So this is one that could be done, I would say, in the short term. Okay, I was just talking now to the possibility to generate pressure in a static way using diamonds, but there is other ways to generate extreme state of pressure and temperature, and this is what is currently developed at the Beamline ID24, where they are currently developing so-called PAM probe experiment using, and they can generate a shock wave using high power laser, typically 100 joule per pulse, a very short pulse of about 20 nanoseconds. And the idea is to generate a shock wave. So you follow, if you have the pressure temperature diagram here, you follow the so-called Hugonio trajectories that brings the material into extreme states of matter. And the idea is when you reach this state, you probe it with X-rays and extract some structural information at the same time. Here you have a nice photograph of the setup, actually this of the setup from the CEA. Okay, and what could we do with this? And one of the natural subject for this kind of experiment is to explore what's so-called the warm dense matter. And what is warm dense matter? I think it's described in this temperature density diagram, where you can see it is a region between solid condensed matter physics, white condensed matter physics, and the plasma state. So it is basically in this temperature regime, actually the temperature is so hot that they are measured in EV. 1 EV is about 11,000 Kelvin. So it's between 0.1 and 50 EV, and a very wide also variation in density from 10 to the -3 to 10 to the 2 gram per cubic centimeter. And this is the region here in green. And in this condition, the materials are partially ionized, partially degenerate. It's a strongly coupled state of matter. And it is, I would say, still, because the interaction are not well characterized, there's still a challenge for theoretical models. And because there's no obvious approximation that hold. And in this case, any data collected in this regime will be very precious. So, and also I would say that there is a huge interest also for geoscience, because here in red in this ellipse, this is the domain of giant planet interiors, such as Jupiter, which is made of hydrogen, for example. So you could actually explore the physics of these large objects. But as a first experiment, we could say that we could restrict ourselves and look at this warm dense matter regime in the pressure regime that is close to the outer core of the Earth. And then in this case, you could explore in these conditions, the outer core of the Earth is liquid, and you could look and extract information about how what is the structure of the local structure of the liquid in these conditions. Okay, this is what I wanted to say about the short-term objective. Of course, there's many other things, but I have lack of time. There's many other experiments that could be done, such as at ID12, where they explore the low temperature physics using low energy X-rays and so on. There's many other examples, but I will restrict to these two for the moment. And I will move on to my next topic, which is the emergence of structural complexity. And I've selected actually three examples, which is three famous examples: the glass transition, and related to this, there is actually the first order liquid-liquid transitions, and I will show you some recent example that was obtained in my group, and then I will tell you about a little bit about polymerization. Okay, what is the glass transition is actually a long-standing and I would say very successful field of research at the ESRF. It was performed, for example, at ID10 to do X-ray photon correlation spectroscopy, at ID18 for nuclear resonance scattering, at ID16. Now ID16 has moved to ID20, but they are actually continuing this kind of research. For instance, to look at the dynamics of glasses and glass-forming liquids using inelastic X-ray scattering. Okay, what is actually the glass transition? Actually, the glass transition, if you look at the standard volume diagram, can occur when, not always, but can occur when a liquid is cooled. If you cool a liquid, it can either form a crystal, if you at the melting temperature, form a crystal, or it can avoid crystallization and become what we call a supercooled liquid. In this case, the liquid remains structurally disordered, and the relaxation time is the time for a system to reach equilibrium. So this relaxation time increases very quickly. And there is a temperature called TG, below which actually the structural relaxation takes such a long time that it becomes almost impossible to observe. And the liquid is then trapped virtually forever in one of the many possible structurally disordered states. Okay, and I would say that the technology of vitrification is actually well known since antiquity, and I can actually show you, there is an example, a nice example of a beautiful example of Roman glass from the 4th century. And I would say also that glasses are widely used in a variety of technical applications. For example, on the Hubble telescope, you have a very large glass lens But still the underlying microscopic mechanism for the glass transition is far from being completely understood. And actually, the reason is actually illustrated here. And it is the question that we could address is why is it so difficult as compared to other phase transitions, such as the solid-solid phase transition, for example, in diamond? Why is it so difficult? And the reason is illustrated here. Actually, I extracted this diagram from a paper by Berthier and et al. And I actually invite you to read this paper because the glass problem is actually very well presented in this paper. And they performed actually two-dimensional liquid and glass simulations from computer with computer, and they could simulate different configuration. And actually, one is a liquid, and the other one is a glass. So I put the A and a B. So in the question and answer, you can try to guess what is what. What is the liquid? What is the glass? So I let you 3 seconds to answer. Okay. Good. Okay. So A is a liquid, of course, and B is I say of course, but it's not obvious at all, because in this case, the relaxation time is 10 to the minus 7 second, and it's 100 of 100 second. So meaning that the glass actually flows 10 to the 12 times slower than the liquid, but both configurations look structurally quite similar. And there is absolutely no obvious other parameter. So that's why this problem is still not completely unsolved. And solving it supposes probably a multi-technique approach, such as inelastic scattering, X-ray photon correlation spectroscopy, X-ray absorption spectroscopy, small and wide angle scattering on the EBS, and also with the help of computer simulations. Just give you examples of experiments of instruments that could be used for such a topic. It's a very important topic. For example, look at the thermal excitations, the phonons, for instance, on ID18, where you have an improved with the EBS, but also they initiated this before EBS, but they have an improved energy resolution of 1 order of magnitude. They go from 0.5 millieV to a 50 micro EV. So there is an improvement of factor 10, and also without any compromise on the intensity, which is quite remarkable. Also, could be used ID28 with a very nice phonon spectrometer that you can see here. It's a beautiful instrument. Also, ID20 could be also employed to look at the electronic excitations. And as you can see, this is also a quite impressive instrument. And coherence experiments could be performed at ID10 for the XPCS, and also on the future ID18, where fully coherence beamline is planned to be built there. Okay, this is what I wanted to say for the glass transition, but related to this, I would say there is the puzzling, so-called first order liquid-liquid transitions problem. And I will give you a very brief introduction. I would say that for the liquid state, if you take a pure substance, until the 60s, the conventional paradigm for these materials was that the pure substance can have only one liquid. So if you look, for example, at the phase diagram of aluminum, you have here a melting line that separates the solid from the liquid, and there is only a continuous variation. And also, the melting temperature monotonically increases with pressure. Okay, that's why actually at this time they called it probably the most boring state of matter. Okay, but things have changed since the 60s. A lot of work have been performed, but to make a very long story short, I would mention only one great result that was published in 2000 by Katayama et al., where they performed absorption and diffraction experiment at Spring 8. And this was actually reported in Nature. And what they've seen is a first order phase transition between two structurally different liquids, as you can see here, a molecular liquid and sort of a polymeric liquid, and with a transition line, a coexistence line, as similar to the one that you can see, for example, in water, where you could observe a variation of about 40% in volume. So this is strongly first order phase transition. It's 40%, to give you an idea. When silicon is considered as a material with a very large volume change when it goes from the semiconductor to metal transition, and it has only a 15%. So this is an amazingly large value here. And this is associated also to very change in the structure factor when we go from the P4 molecules to this polymeric state here. Okay, and also I would say that there was a lot of activity regarding for the theory part, where first order liquid-liquid transition were predicted in the stability, in the liquid stability field for several important systems, of course, including hydrogen, nitrogen, and CO2. I don't need to convince you that those systems are extremely important. But I would say, for example, if you look at the phase diagram of hydrogen, now I'm in the liquid state, so there's a prediction from a transformation from liquid H2 for molecular H2 to atomic liquid here with the presence of actually critical points here. But I would say that unfortunately this system are extremely challenging. It's not only because you have to generate both pressure and temperature, maintain hydrogen in these conditions without making it reacting with the confinement material and so on. So those experiments are extremely challenging. And on our side, on BMI 2027, and in the framework of the thesis work of Laura Henry, actually she's now moved as a postdoc in Soleil, we looked at sulfur, and actually sulfur was very interesting because sulfur and phosphorus, actually they have important similarities in their phase diagram. They both have molecular and polymeric forms in their solid states. And also there is a so-called lambda transition here in the liquid state that is known from many years, where you have molecules that opens up to form long polymeric chains. And also that this kind of systems, because of the presence of large polymeric units, is too complex for ab initio simulations and was not actually approached by this kind of simulations. So the questions that we actually addressed at the beginning of this work was also, does sulfur undergo a first order phase transition? And if the answer is positive, does it exhibit a liquid-liquid critical point? And this would be the first example of such a liquid-liquid critical point in an element. And actually, it's what we did. And also here, I will not enter too much into the details. I will give you just the final results. And actually, we could evidence a liquid-liquid first-order phase transition using actually density measurement by X-ray absorption. We also confirmed this transition using X-ray diffraction and Raman spectroscopy. And as you can see here, it was also confirmed by X-ray imaging. And actually, I have chosen, I will show you a little video. And if you look at the pressure temperature phase diagram here of sulfur, we define a line here. We could find a line between the low density liquid, which is composed of a mixed molecular and polymeric phase, to purely dense, purely polymeric phase, which is called the high density phase. And in principle, if you cross this line, just by increasing the pressure, you should see some density contrast at this point. And in principle, you should see it if you could perform radio X-ray radiography in situ, you could see some change, some clear change in the sample. And as you can see here, this is the sample contained in the pressure vessel that we see in transmission using X-ray radiography. And as you can see in this movie, you can see clearly when we cross this line, a bubble of the high density liquid growing into the high density liquid. And this was actually a beautiful demonstration of the existence of this phase transition. And also, we could also measure here a critical point similar to the one that exists, in water, for instance. And there's actually this paper, there is a paper that will actually come probably next week in Nature that describe this work. Okay, but still there is some open questions. So the question we can address is, why is this type of transition so rare? There's so far only two systems, phosphorus and sulfur, that exhibit this kind of transformation in the stability field of their liquid. There's other systems that show this kind of transformation, but it's in the supercool regime. So only two cases in the stability field of their liquid. So the question we could address is, what are the driving forces of the transition? If you look, for instance, of the transition liquid gas transition in water, it's fully driven by the density variation. But here it's not the case, apparently. So we have to look more into the details. And of course, is there some similarity with the glass transition? And finally, since we determine this critical point, what are the physical properties of the liquid in the vicinity of the critical point? What are, for instance, what we call the critical exponents for this kind of transition? Do they compare well with the case of normal liquids, such as of gas liquid transition, such as in water, for example? So all kind of information that could be extracted in the vicinity of this point. Okay, and the final subject I would like to touch is actually polymerization, and this concerns, for example, the transition from a simple molecular system to a polymer, or to a mixture of molecular species and large polymeric assemblies, such as, for example, here actually at the room pressure, actually sulfur undergoes a so-called Lambda transition, where the S8 molecule opens up to form very large polymeric assemblies. I would say, as mentioned before, this transition is not correctly described in the framework of the Ehrensfest classification, or by Landau's theories, or any theories, actually. And the underlying mechanism actually is unknown. And I would say that also this is too complex for state-of-the-art ab initio simulations. So again here, probably looking at this kind of object, to look at the emergence, what I call emergence of complexity, when you go from a simple system to a more complex system, this will certainly require, again, a multi-technique approach. And this could be, for instance, done at the beamline ID2, where you can perform in situ multi-scale SACs, small angle scattering and wide angle scattering. So you could look at the small object and big objects at the same time. This is exactly what we need to look at this kind of physics. And I would say that, as mentioned before, because it's too complex for standard molecular dynamic simulations, this will probably also require the latest development for ab initio simulations that involved the artificial intelligence and machine learning. Okay, and I think this problem is really important if you look at the pyramid of complexity from molecular system up there to cells and individuals and even community. The first tile of this complexity pyramid is actually defined here with this transformation from simple object to much more complex object. What are the parameters that are involved? Is it entropy, density? What kind of information could we take? Because then if we solve this problem, we could probably enter and give more insight into the problems that are even more complex when you go up into this pyramid of complexity. Okay, and I think with that, I will now just give a few words of conclusion. And I'm convinced that EBS will have a strong impact in the short, medium, and long term. And I hope I convinced you through these few examples. I would say that the problem in hot condensed matter are really complex and certainly will require multi-technical, multidisciplinary approaches. And this will also go in parallel certainly to the progress that we could be made in computer simulation, in particular with the current developments of quantum computers and artificial intelligence that will probably help solving these really long-standing and important problems. And with that, I think I will thank you for your attention. I will give the words to Patrick. You are mute, Patrick. Still.
Thank you very much, Mohamed, for the beautiful presentation. It was a nice challenge, and you made it beautifully. So, question is now with the talk is open for discussion, and there are a few questions already coming in the box. So I explain again for everyone how to ask your questions. There is a box, question and answers, where you can type in your questions, because you are not on sound, and questions can be upvoted so that you can prioritize questions for that you would like to be answered. And so, Mohamed, there are a few questions concerning the diamond Anvil cell. And the first question is that some people would like to have a better understanding of how it is made, what is the structure. The question says, in the toroidal Anvil cell, how do you, well, no, what is the shape of the diamond? Is it toroidal? I guess no, but please explain.
Yes. Okay, so first, the basic question, well, what is a diamond Anvil cell? It is a very simple principle. I mean, it is based on a very simple principle, which is the pressure is equal to the force over the surface. So if you actually want to reach very high pressure, you need to much reduce the surface, and to reach this high pressure, you need a material that can sustain it, and the natural material for that is diamond. And the principle is very simple. You bring two diamonds together in position, and you just push on the back of the diamond, and by intensification you can reach extremely high pressure. But the tip of the diamond is of the order of 200 micron or less, and in this case you can reach enormous pressure. And that, as I mentioned before, the maximum pressure that we could reach with the standard shaped diamond, which is called with faceted diamonds. Actually, there is a lot of literature on this. Is limited to about 400 GPa, 380 GPa maximum, and after you reach the concentration of stress on the head on the diamond is so high that you break it. So if you want to reach higher pressure, and this was actually the paradigm for the last 40, 50 years. But recently, with the development of techniques such as the fast ion beam techniques, we can actually shape the diamonds to any type of shape with a high precision. And actually, the group of Paul Hubert developed this what we call toroidal. But what is toroidal is not the diamond; it's the gasket that contain the diamond. So the idea is here that every diamond there is no sharp angle. It's just smooth surface, smooth distribution of stress that makes the diamond going much higher, because you don't reach the concentration of stress that will kill your diamond, despite the fact that the diamond is the hardest material. So this is how we can reach this very high pressure. And what was the second part of the?
And the other question that was asked is how do you estimate the pressure in the cell, in the diamond Anvil cell, and the same for dynamic compression?
Yes, for static experiments, there is several methods, but the most standard one is called the ruby fluorescence method. So inside the cavity next to the sample, you place a little ruby chip that is a few micron, and also it's another advantage of the diamond. Diamond are transparent, so you can go through them with X-rays, but you can also go through them with lasers. And so the idea is here to measure the pressure. You have this little ruby, and you can excite the fluorescence of the ruby. And the way this fluorescence line moves with pressure is calibrated. And another way to measure the pressure would be directly with X-ray diffraction, because with X-ray diffraction you can see at the atomic position, and you can actually see how the atoms moves as a function of pressure. And this follow a law that is called the equation of state of the material. So if you measure the volume of a material at a certain pressure, you can actually calculate the pressure. Okay, in the dynamic experiment is more difficult because you have it's called the experiment. The pressure and temperature are linked. You can follow the so-called Hugonio experiment, the Hugonio trajectories in the pressure temperature plane, and there is by the principle of conservation. You could actually one of the parameters that is extracted from that is the pressure. So if you measure directly from the so-called VISA interferometry measurement, you could extract the pressure.
Thank you, Mohamed. Then there is a question, a very popular question about hydrogen. And the question says that X-ray measures electronic densities and hydrogen has only one electron. So can one still do the structure determination at extreme pressure and temperature with hydrogen?
Yes, that's why actually it is one of the challenges for IBS. Of course, it has only one electron, so this is the most difficult samples. Also because it's highly reactive, but one of the biggest challenges is also because the diffusion, the X-ray diffraction is very weak in the case of hydrogen. But what helps is that we had high density. So by increasing the density, you will have more electrons in the probed volume. And I would say that actually this was done up to 3 megabar. The structure of hydrogen, they were solved already. So this is not an impossible challenge. I would say that going in the era of 400 GPa, the sample gets even smaller. So to probe such samples, we will need a very, very small beam. So typically 150, 250 nanometer beam that will be necessary to probe such sample. And yeah, it still remains challenging. That's why it's not certain. And also there is one more, I would say, problem that is conceptual, because if you go into it is predicted that at a certain point, hydrogen will become atomic hydrogen. In this case, the so-called structure factor theoretically become flat. And in this case, we will not be able to see any signal. But the prediction for the first prediction is at 450 GPa is that for a molecular system. In this case, you will still have some structure and we will be able to measure something.
Maybe to continue with hydrogen, there are, of course, expectations that metallic hydrogen would be a superconductor. How would one be able to demonstrate superconductivity in a diamond Anvil cell?
This is actually done, and there is a group in Germany by a very good group of Emergence that what they do is they conduct electrical measurements in the diamond cell. So it's possible to do that using the four-wire technique, where you can put 4 wires, you can measure the current and look at the resistivity or as a function of pressure. And it's how actually they measure the superconductivity in these hydrogen hydrides, for example, lanthanum hydrides with superconducting temperature close to 260 Kelvin, but it was at very high pressure, I think above 150 GPa, 160 GPa, something like this. And they could actually do this superconductivity for hydrogen.
So there are some contacts that go through the gasket?
Yes, but the gasket is insulating. It's an insulating.
Yeah, but okay.
Yes, and there is some contacts that goes through the gasket. But also another method that was very elegant method that was developed at ID18, also group, I think, is to exploit the so-called Messner effect, where when material becomes superconductor, there is an expulsion of the magnetic field. And so by putting a little piece of nickel and using the Moss-Bauer technique, where you can actually measure the magnetic field, they saw a vanishing of the magnetic field when the material goes in the superconducting state. So you can actually, with X-rays, you can determine if a material goes superconducting. So these are two methods. Both are very challenging and very elegant.
Thank you, Mohamed. There is also a question about whether phase transitions upon increasing pressure are reversible or irreversible when you go down in pressure, in the case you have been discussing.
Well, it depends on the material. Most of them, I would say, are reversible. But if you look, for example, at the transformation of diamond, you can wait forever, but the diamond will not revert back to graphite. So this is one typical transformation that is irreversible. And the reason is because the kinetic barrier to overcome is so high that basically the system stays in this state forever. And diamonds are forever. So, but they are they are high pressure items to products. But there is other transformation. For example, if you compress iron into this so-called, it has a FCC to HCP transition between two structures that are very close. This transformation is fully reversible. So you have all kind. It depends on the cases.
There is also a question about critical behavior of the liquid-liquid transition, and Narayan would like to know whether there is a reason to expect deviation from Ising model criticality.
A priori, there is probably not a good reason to think that there is a deviation from the Ising model, because this is correspond also to the class of universality. But this has to be checked, because in the case, this is the first example of a liquid-liquid transformation. So the density difference is much smaller than when you have a gas-liquid transition. So the correlation lengths and the fluctuations might be different. So we could expect some behavior that is different. And this is actually one of the questions that needs to be answered, whether we are in the same class of universality as for the liquid gas critical point, or if we have a different behavior. So there's no, for now, theoretical description of this kind of singularities, but this is something to work on.
There is then a question about whether the increased flux density could be detrimental to the samples.
I would say it depends on the samples. If you have, for example, in physics, we are working on inorganic systems, mostly on inorganic systems, and I don't think there is a big problem with inorganics. The problem is for organic samples that are. We know that there is a big problematic. Actually, it was a full workshop on this that was organized by Peter Glatzel recently. To evaluate how materials can sustain this high flux, and most problem could arise for organic materials. Already with the current machine, you have to cool down the organic material to actually extract the information before it dies. So if we increase by a factor 100 or 1,000 on this type of materials, of course we could end up with problem. But in most of the problem, I would say, in most of the cases, this could be solved. Of course, this is something challenging, and there is some work to be done. But I would say that it's always possible to reduce the flux, but not to increase it. So. This is a bit provocative, but in this case, we will have a machine that will produce as much as photons. So we have to find solutions, basically, to work even with the more sensitive samples.
Okay, and then the final question will be: will we be able to reach metallic hydrogen at ESRF soon?
Yes, of course, tomorrow.
Okay.
No, I don't know. I mean, this is by the essence of research. We want, this is an objective, of course, but yeah, we will see. This is actually the good news is that we can, now it's possible to produce this sample. Measuring something quantitative on this sample is a different question, and we want to address it. And this is something very challenging and very exciting, I would say. But I cannot give a definitive answer on this.
So with this, I think we have to close the discussion. I thank very much Mohamed. I also take the opportunity to acknowledge we have that this series of webinars is supported by the Streamline project of the European Union. And I invite you all participants to join us again next week and weeks after for the next webinars of this series. Have a nice day.
Yeah, you too. Thank you.